This is High Technology High School Team 2854 from Lincroft, New Jersey. So the first question in the Moody's Mega Math Challenge is, tell us your name.
Hi, I'm Ruby and I'm a junior from High Tech.
Hi, I'm Cynthia and I'm also a junior at High Tech.
Hi, I'm Austin. I'm a senior at High Tech.
Hi, I'm Patrick and I don't actually go to High Tech.
I'm Zachary. I'm a senior at High Tech.
Great. Welcome, and you may begin.
Good morning. We're Team 2854 from High Technology High School, and today we present to you our solution to the 2014 Moody's Math Challenge. First, we developed a model to determine the number of calories a student would need at lunch. We considered numerous factors such as age, gender, height, weight, lean body mass, and other lifestyle influences. We then utilized the current guidelines and the previous model to determine the percentage of students whose needs are met by the current policy. We then used the constrained optimization model to create lunch plans with weekly budgets of $6 and $7 per student that maintain nutritional standards. We then performed a sensitivity analysis on this model. With these results in mind, we recommended certain modifications to the current system.
The first step in assessing the HHFKA was to determine whether or not it would meet the energy requirements of the students. To do this, we wanted to find basal metabolic rate, or BMR, in terms of kilocalories per day. We split this task up into three main parts, finding BMR based on growth rate, based on height and weight, and based on lean body mass. First, we looked at growth rate. Because we were assessing children rather than adults, growth rate was an especially important factor to consider when finding BMR. The World Health Organization provided us with height for age graphs of both boys and girls aged 5 through 19, and observing these graphs, we found that children of this age range exhibit three main patterns of growth: pre-adolescence, adolescence, and post-adolescence. In both pre-adolescence and post-adolescence, the height for age graph was approximately linear. Therefore, the growth rate was constant. However, during adolescence, the height for age graph was logarithmic. Therefore, the growth rate was variable. Because we wanted to be able to assess a large sample of students across the United States, we wanted to be able to find the growth rate, and thus the BMR, given only the child's age in years rather than the child's age in years and months and days. Thus, we constructed a piecewise linear function by linearly interpolating the height for age for each year during adolescence. Thus, the final growth rate was a step function, as seen here. To find BMR, we took this growth rate, GR, and divided by height, H, to find the percentage of growth. We then multiplied this by E, a value of 3,200, which represented the average energy expenditure for each percentage of cellular growth needed every day. This consisted of two parts: the energy needed to synthesize tissue and the energy deposited into that synthesized tissue. The next factors that we looked at were height and weight. The Institute of Medicine conducted chemical tracing tests to determine the constants by which height and weight were multiplied by to most accurately determine BMR. It turns out in females, BMR is more greatly affected by weight, whereas in males, BMR is more greatly affected by height. By multiplying these constants, neither kilocalories per day per centimeter or kilocalories per day per kilograms, by height and weight respectively, we were able to find BMR. The final factor that we looked at was lean body mass, or the body composition of the child. Because a child with more lean muscle would end up burning more calories in one day than a child with more body fat. This was due to the fact that 1 pound of lean muscle burns approximately 6.5 kilocalories a day, whereas 1 pound of fat only burns 2.0 kilocalories a day. All the previous calculations we did were on the average child, thus we wanted to compare the body composition of the child we were analyzing and the average child. To do this, we took the difference in body fat percentage between the child and the average, which was 17.5 for females and 12.0 for males. We multiplied this difference by weight, W, to find the lean body mass in kilograms by which a child differed from the average. Then we multiplied this by 4.5, which is the difference in energy expenditure between lean muscle and body fat. Then this correction factor for BMR was made negative, so that a child with a greater body fat percentage than average would expend less BMR in one day. These three factors, growth rate, height and weight, and lean body mass, were added to yield the final equation for BMR.
So in addition to BMR, we also had to take into consideration other lifestyle factors such as physical activity. So to begin, we used the constant K sub activity, And in the Harris-Benedict equations that normally calculate the number of calories you need per day, this represents how active a person is on a scale of 1.2 to 1.9, and these are normal bounds for the variable. However, instead of estimating the value of the variable, we decided to make an actual function for it to see how it would work. So we assumed a normal distribution model, and we said that 1.2 and 1.9 represent the normal balance, or two standard deviations away from the mean. And if we do this, we find that we have a normal distribution curve with mean 1.55 and standard deviation of 0.18. And now, in order to graph you on this curve and find your K sub activity, we have to find your z-score, or how many standard deviations you are away from the mean. And to do this, we take the time you exercise, subtract off the national average of 60 minutes per day, and divide by the standard deviation of 15.8. Thus, we get how many standard deviations you are away from the mean, and thus we can graph you on the normal distribution curve to find the exact K sub activity. In addition to this, we also have to consider other meals and sleep. So the interesting thing is you have a total number of calories you need per day, but not exactly per meal. So the number of calories that you need can be made up of calories during breakfast, lunch, or dinner. And although we'd like to increase the number of calories we provide during lunch to support those who may not get enough during breakfast or dinner, the problem is an excess of calories consumed in a single sitting may cause students to become sluggish and unable to learn. Thus, we cannot drastically increase the number of calories that we provide during lunch. And finally, we have the effect of sleep. The interesting thing is a study done by UPenn found that the effect of sleep can be considered a binary variable. So if you are sleeping enough, more than the recommended 8 hours, you find that the number of calories you need is based on the BMR and your physical activity. However, as soon as you're sleep deprived, even an hour, 2 hours, however long, you find that you need 20% more calories to get you going through the day. And thus, we simply stated that sleep was a factor that was either 1.0 or 1.2. Now, taking all these factors into consideration, we found our final equation. The total number of calories is the K sub activity multiplied by the K sub sleep multiplied by the BMR. And from this, we find that we can take into consideration your height, weight, and a variety of other factors to produce an accurate number of calories that you need going through the day. Now, using this final equation, we had to determine who's actually getting enough from the proposed 750 to 850 calorie lunch plan. And to do this, we began with a simple random sample of 500 students. And we first tackled the issue of sleep. So we conducted a T-confidence interval suggesting that the mean hours of sleep time is significantly less than the suggested 8 hours, or that most high schoolers and other schoolers are sleep deprived. And when we conducted the confidence interval, we found that 0 did not fall within the constructed confidence interval, and thus there was a significant difference. Now, when we went back and checked our simple random sample of 500 points, we found that very few of them actually got enough sleep. In fact, less than 10%. Now, assuming that the majority of high schoolers are sleep deprived, we find that our proposed 750 to 850 calorie lunch plan will actually support a negligible number of students, almost 0%.
Now, despite this rather foreboding news, we next attempted to create a model that would generate a sample lunch plan for a school that would both fulfill the USDA's nutritional requirements and the school's budgetary constraints of $6 or $7 per week per student. However, it soon became clear that we had to ask ourselves a question, whether or not students would actually eat all of the food they were given. And it makes a kind of intuitive sense that they wouldn't, since to use a rather trite example, if you give a student a pound of candy and a pound of spinach, well, obviously they're going to eat more of the candy than they are of the spinach. And indeed, that's borne out by the literature. In this study done by Juliana Cohen, which found that the USDA's guidelines did, in fact, lead to a significant amount of waste, where waste is defined as food thrown out instead of consumed. So to account for this, we introduced a unitless scaling factor P, which is the proportion of food students will consume over the entire population of students. Now, P is based upon the chemical and physical composition of individual foods, and as such needs to be calculated for each food individually. Now, how do you do P? Well, P is related to attractiveness, and attractiveness is also related to taste. So we created a taste function. Now, what is taste? How do you quantify it? There's 5 tastes, so to speak: sweetness, saltiness, bitterness, sourness, and umami. However, in the literature, it soon became clear that there were really 3 dominant ones which we had to concern ourselves: sweetness, saltiness, and bitterness. So to construct a taste function, we looked at the chemical and physical compositions of the foods and made physical analogs for each of the tastes. So the taste function was a scaling factor times the physical analog for sweetness, which was sugar per cup, plus a scaling factor times the physical analog for saltiness, which was sodium per cup, plus another scaling factor times the physical analog for bitterness, which was calcium per cup. We then calibrated this function, also fitted into the form of P you can see at the bottom, 1 minus e to the negative taste, with Cohen's study on the USDA's guidelines and how they pertain to food waste ratios. And we calculated across entrees, fruits, and vegetables, and we were able to generate these three values for the scaling constants, where A and B were positive and C was negative. Now, as I said in the last slide, P is of the form 1 minus e to the negative taste, which is an exponential decay function. We use that function because the proportion consumed drops off rapidly with decreasing attractiveness, yet stays relatively high with higher attractiveness, so that worked well. Because we had 3 inputs and 1 output, the easiest way to generate graphs was to hold 2 of the inputs constant and let the other one move over a range of values. So the graph you can see on your left, saltiness and bitterness were held constant and sweetness was allowed to move. The one in the middle, saltiness was allowed to move. And the one on your right, bitterness was allowed to move. And you can see the end behavior for each of the tastes.
We then incorporated this caloric scaling factor into our overall model for lunch plans. Mathematically, we found that the best way to represent a lunch menu was a linear combination of items, where each of the items corresponded to an item on the lunch menu, and the linear coefficients corresponded to a number of servings per week. We then solved for a result by performing a constrained linear optimization, where on one hand, we sought to maximize the number of calories we can offer to students, and at the same time, ensuring that we satisfy nutritional, price, and repetition constraints shown here. The first 6 are nutritional constraints given by the United States Department of Agriculture, and these are derived from the various food groups in the food pyramid, as well as one constraint of sodium of 3,200 milligrams per week per student. The next is a cost constraint derived from the budget of either $7 per week or $6 per week per student. And finally is a servings constraint. When we evaluated the USDA's sample lunch plans, we found that each item was repeated a maximum number of twice per week, and thus we sought to incorporate this assumption into our model, as students will become bored of having the same item too many times per week. Shown here is a partial output of the model for one particular case, K through 6th grade level and $6 per week budget. And as you can see, the model produces a numerical amount of each menu item to serve per week. Here, the model suggests that the school serves 2.0 servings of turkey sub per week, but a relatively lower amount, 0.3 servings, of the relatively lower nutrition burrito. And thus, the model indicates the optimal menu amount over a week for a school. In practice, what a school can do is take the food provider options given by the distributor, run it through the model, and then use this to generate an optimized meal plan for their school. Here we took a look at the model across all the grade levels proposed to us and on both budgets, $6 per week and $7 per week. Shown in blue is the model output in terms of the total number of calories per week we can offer to a student. And shown in orange is the deficit between this model output and the previous model's prediction of the amount of calories students will need to consume. And as you can see, there's a large issue here in terms of large caloric deficits. The model predicts that no student will receive enough calories. In fact, even the best case scenario, students receive only about 50% of the required calories, indicating a significant problem with the act, and thus concluding that the act is ineffective. In order to find ways to resolve the situation, as well as to ensure the validity of the model, we performed sensitivity analysis, where we took each constraint and shifted it positive and minus 20%. We found that the greatest impact was held by changing the USDA sodium limits and changing the USDA grains minimum, and thus by imposing regulatory changes that change these constraints, we can most effectively increase the amount of calories we can offer to students.
Given more time and data, we'd like to look at how medicine, supplements, and stress affect children's basal metabolism rate. We'd also like to look at how common food allergies and other dietary restrictions could help produce a more comprehensive meal plan. Because the price and availability of food differs across regions, $7 in New York might not go as far as it would in Topeka, for example. Taste itself also varies from region to region, and taking this into account would impact the lunch plans generated. Thus, geography could help produce more refined meal plans. Other studies on factors such as advertisement and brand recognition could help make meals more appealing. In conclusion, the Healthy Hunger Free Kids Act is largely ineffective. For students with adequate amounts of sleep and minimal physical activity, these lunches barely meet caloric requirements. However, the reality is that most students are sleep deprived and do have some form of physical activity, and therefore the 750 to 850 calorie range is not enough to provide for the average student. If the policy is still to be promoted, we encourage low-sodium foods as well as increasing the appeal of meals offered. In short, we recommend the reevaluation of the Healthy Hunger Free Kids Act. Thank you.
Okay, I'll go first. I have a couple of questions, actually. The first one is related to your activity coefficient K, and you used numbers 1.2 to 1.9 and said they were within 2 standard deviations from the mean. What made you say that? Are you making that assumption from something you've seen? Did you know that it was a normal, these things had a normal distribution?
Yeah, so what we did first of all was we looked at previous equations that had been used to calculate the number of calories that you need. And when you go back, you find that there are several sets of equations, one of which, like the most accurate currently used, was the Harris-Benedict equations. And from there, they applied this such factor, K sub activity, and they said that for a normal population, like the lower bound would be 1.2 and the upper bound would be 1.9. And when you look at the data of how much people exercise in the United States, you do find that it follows a normal distribution curve, and thus we can say that 1.2 and 1.9 are 2 standard deviations away.
One other question I'd like to throw out there was regarding the, you said you constructed a confidence interval, but you were testing hypotheses that the mean was 8 versus less than 8. And yet you say 0 did not fall in the confidence interval. Wouldn't it mean that 8 didn't fall in the confidence interval, or did you do something different? I don't know what you did the confidence interval on to get the
Oh,
fact
I'm
that
sorry.
0.
I believe we did it between the difference in hours of sleep time and 8 hours to find that 0 would then be pretty much in the middle.
Good. Yeah, that's right. Thank you. That's a good answer.
Okay, I was looking in your summary, and in your summary, the ranges of caloric needs that you got using the first part of your model were somewhere covered by 750 to 850. The ranges that's comfortably in the middle of that. And then later you were talking about how 750 to 850 calories is not enough.
Because in order to find that 750 to 850 calories would satisfy requirements, that's assuming the ideal conditions such that K sub sleep is 1 and your activity constant is at 1, which is far below the normal. And using these factors, we find that yes, for younger age groups, the 750 to 850 calorie lunch plan would support them, but these conditions simply won't exist in the real world. You find that many kids, A, are getting far more than subpar activity per day, and you find that most of them are getting close to 8 hours or less sleep than 8 hours. And thus you find that these conditions don't actually uphold in the real world, and thus the 750 to 850 actually would not satisfy any requirement or any of their requirements.
Okay, I have a question. I was really interested and really liked your approach towards taste and focusing on taste in your paper. One thing that I was not surprised by once you worked everything out was the negative coefficient that was associated with bitterness. Right? It's not going to be some big surprise. I think we can see that happening. But then I feel like that leads to a sort of an obvious follow-up question of how that's going to relate to actual development of a meal, right? A menu plan, when you're basically saying vegetables bad, right? So how do you address that?
Question. So here.
Okay, right. Like as you said, the bitterness curve is more or less down, which would lead to the paradoxical conclusion that in order to get people enough food, you need to give them really, really unhealthy food, which really isn't an optimal solution. We suspect that the answer lies in food preparation. Since you can prepare food that even, like vegetables, if you prepare them a certain way, like let's say you just boil a head of broccoli or a head of cabbage, whatever it's called, then no one's really gonna like it as much. But if you prepare it in the correct way with special sauces, I'm not a chef, but if you prepare it in the correct way such that it's still healthy, it can also taste good. So we suspect that's the way out of that paradox.
Okay, thanks.
Can you talk a little more about what you discovered about students who don't eat breakfast in terms of the impact on their caloric needs.
So ultimately, the problem is that not everyone in the United States gets enough calories per day. Like they, as you said, don't eat breakfast, maybe they don't get enough during dinner. The issue is that we can't actually supplement that by increasing the number of calories per lunch because that would negatively affect them in schools. So the only sort of way around that would be to give snacks, give other sort of sub meals throughout the day, but not give it to them in one large sitting.
Thank you.
Thank you very much.
All right, thanks a lot.
Thank you.